Okay, welcome to this video on some more advanced topics in phase diagrams. We'll see more complex systems, including the phase diagram for low carbon contents irons or the stainless steel series. So let's remind ourselves some tools that we have. We learned the utility of tie lines in estimating the content of two phases in a phase field like that shown here for the copper-nickel system. So at point A, if we've got a sample that overall is 35 weight% nickel, up at point A, the full liquid molten state, we would have uniform liquid with randomly dispersed metal atoms of copper and nickel in a disordered fluid or liquid. When we consider other options like points B through D, we will start to observe some two-phase scenarios where we're in the white domain of the phase diagram. Notice again that we're only in a bit of a zoomed in area of the full diagram here, between about 20 and 55. And as we go to lower temperatures, we see that the bottom phase field is only solid alpha. So let's consider point B and see if we can answer this question. So it asks us to determine the weight% of nickel in the materials that occur at point B and D. So looking at point B, it looks like we are in the two-phase phase field that contains both liquid and alpha. And so we can use the tie line to help determine this. So let's start with the alpha phase. So the alpha phase, we'll use point B, and then we'll walk over to the boundary, the solidus, and where our tie line intersects that in our isothermal tie line, we know the composition of the alpha phase, therefore. So the alpha phase here is 46 weight% nickel. The liquid phase at point B is, we'd use the tie line and we walk back the other way. So that takes us to the 34 mark, a little lower than the bulk average. So we are 34 weight% nickel in the liquid at point B. Point C, lower the temperature still. And so here you can see, again, we're in the white area, so we expect alpha. And we can look to the tie line as we go to the solidus again. And so here we intersect in the isothermal tie line at 43. So we are 43 weight% nickel this time. And the liquid, formerly 34 at higher temperature, should likely change. And so when we use that tie line, and this time we walk all the way to the liquidus and intersect that boundary, we can see that the nickel here is, nickel content is 32 weight% nickel. Okay. And then lastly, I think we're asked about point D, which is just at the lower boundary. And again, there's going to be an alpha phase, and so we can use that. So we're going to, again, walk all the way to the liquidus, and so solidus, and we're going to see 36 weight% nickel there. And then if we walk all the way to the liquidus, where we intercept that phase boundary, we're going to see that the liquid here is 24 weight% nickel. Okay, so hopefully you were able to do that as well. Point E, we've crossed right into the alpha phase entirely. And so this is now a solid, pure solid, and so there's only alpha. And of course that is going to match the composition of nickel, which was 35 weight%. Matching that we had at point A, which was way up top. So notice that as we've gone from point D to point E, we've lost all of the green, and we've now coalesced blue sections into a polycrystalline solid where there is no green liquid phase. and number of grains. In this zoom up in our cartoon, we're seeing 4 grains here at point E. Okay. Good. So just to formalize all that and put it in kind of cleaner writing if you want, we have all those answers here again. Okay. Second, see if you can do the similar points, but what we want to determine is the amount of each of these phases now at points B through D. So hopefully it's obvious to you that at point A, there's only liquid, so the weight content, the weight fraction of liquid is going to be 1. Okay, so the weight fraction is going to be equal to 1.00. Of course, multiplied by 100%, we would have 100% liquid, therefore, at point A. Point B, we're going to be able to use our tie line to do that as well. So take a moment to pause the video if you want and see if you can determine the weight fraction of alpha and liquid at point B and advance to point C, D, and eventually E when you're ready. Okay, so using point B to determine the weight fraction of alpha, we're going to use our tie line segment. And so while we're interested in alpha, we're not going to use the right section of the tie line, but the tiny section of the tie line. So that is, we're going to go to the left this time and intersect the liquid phase. So our numerator for this is going to be 35 minus 34% for our x-coordinates for the little segment. And then we've got to divide through by the full length of the tie line. So that's going to be the 46 minus 34 this time. And so the weight fraction of alpha here should be 1 divided by 12. And we should be 0.0833 weight fraction in alpha. Weight fraction in the liquid at point B, we're now going to use the longer segment. So that's going to be the 46 minus 35. So that's, and then divided by the same denominator. So this time we're going to have 11 divided by 12, which of course should be the makeup for the fraction to the alpha. And so 11 divided by 12 here is 0.9166 weight fraction. Okay, for C, similar, so we'll have similar approach but different answers. So this weight fraction is going to be, for alpha, we're going to have 35 minus 32. That's going to be 3 over the full length now. So 43 minus 32 is 11. And in this case, that alpha corresponds to 3 divided by 11. And we've got the 0.27. You see it here. And for the liquid fraction, we're going to have the same denominator, 11 this time, and we're this time going to use the opposite tie line, so we're going to go all the way this way. So it's going to be 43 minus 35, which of course is 8, divided through by the same denominator, and it should be the complement to the 0.27 that we had a moment ago. So 8 divided by 11 to give us the 0.73 that you see here. Okay, so look at our cartoon at this point. While we have it from the previous slide that we knew the nickel content, you can see here now as our cartoon is indicating that whatever alpha phases we did have, that they are much more plentiful, as indicated by the change in the weight fraction of the alpha from about 8.3% to this time 27%. Okay, and then point D, you can see we would have a similar procedure there, alpha and L. This time our denominator is going to be 12, and our numerators are going to be, for the weight fraction of alpha, we're going to be 35 minus 24, so this time it's 11, and we're going to be 1. So 1/12 and 11/12 are our fractions there. Notice that these points at D are opposite in weight fraction to what we had at B. And then when we go to point E, there's only a single phase, so again, we expect that to have a weight fraction that, for the alpha, that is everything, and so that's going to be 1.00, or 100% by weight alpha in that area. Okay, so hopefully you got those answers. So here they are presented to you again, just formalized a little more cleanly for you. And we've seen how we can quantify weight fraction and how they've changed throughout. So notice how the weight fraction of alpha, for example, has gone from 8% to 27% to 92%. And in those transitions, we'll go back. So the alpha was 46%, and then it became 43, and eventually 36 for cases that had a weight fraction that was equal to 8%. Weight fraction alpha here equal to 27%, and then eventually weight fraction alpha here of equal to 92%. Showing it all on one slide there. Good. Okay, so with that behind us as a bit of a refresher, let's consider some other options. So we saw and tracked what happens as we take a sample at about 35 weight percent nickel and cooled it to various points, and we sort of observed changes here in the microstructure for the two-phase system in the two-phase field shown here, where we have both liquid and alpha. So we've seen that the concentration of alpha changes as we solidify. We've seen that the first alpha that formed had a concentration that was pretty high in nickel content, about 46 weight percent nickel. And then towards the bottom condition at around point D, the concentration was much lower, on the order of 35 weight percent. So these calculations are for what we call equilibrium structure conditions. So that is where we've allowed all phases to re-equilibrate the nickel content per the information in the tie line approach. Okay, so that is, if we were to inspect one of these tiny little alpha particles and look and map by, say, a color shade for all the content that is 36 weight percent for nickel at the point of around D, we would see that the whole particle, the whole alpha particle in this little red area, is all uniform in its nickel content as estimated by the tie line approach of 36 weight percent. Now, for a condition that's had fast cooling, we can use the information that we had before to understand that we're going to see more of a chord structure this time. We knew the first particles that formed were rich in nickel, and the last were more deficient in nickel. So that is, the center of the alpha particle that forms, if we have a fast cooling, should have the highest nickel content, And if no equilibration happens, we will not be able to achieve a core that has the 36. It'll be maintained at that higher 46 weight percent nickel. Okay, so that is the first particles that form will have 46 weight percent. And then again, as new alpha particles add on, they will be in line with the nickel content that was created last from our equilibrium conditions. So we'll be very high in nickel content in the middle and lower in nickel content towards the outside. So notice this chord structure is quite different than the equilibrium structure that we see contrasted from right to left there.